Assalamualaikum and a very good day. I bid to our beloved lecturer, which is Dr. Faisal and Dr. Said. We from Group 5 are going to present our project. There were 5 members of our group, which is the first one is me myself, Azami. Second one is Ellie. Third one is Hafiz. Fourth one is Dia, and the last one is Anis.
Assalamualaikum and hi, my name is Siti Nurmada binti Masham. My metric number is CF330072. I will present translating engineering theory into structural reality. So on this slide, I will explain the overall workflow for our project, which consists of 3 main stages, which is design, simulate and validate. So the first one is design stage. We constructed a physical bridge model using balsa wood based on the Warren Truss configurations. So during this stage, we ensure that the bridge follow all the required dimensions and metric constraint while maintaining inefficient structural design. Next is simulation stage. We create a digital model using StartPro and also perform a manual analysis using the method of join. This analysis allowed us to determine the internal force in each truss member, calculate the support reaction, and predict the structure deflection under 0.048 kN dead load. And the simulations identified which member were in tension and which were in compressions. Finally, the last one is validation stage. We test the actual bridge, which is the balsa wood bridge, by applying load until failure occurred. Then we compare the experimental result with our theoretical calculations. The close agreements between both results show that our analytical model accurately predict the real structure behavior of the Warren Truss. Next slide is the geometrical efficiency of the Warren Truss. So this slide explains why the Warren Truss is considered one of the most efficient truss design. The first advantage is pure axial force. Because of its retrograde geometry, most members carry either tension or compression only. This signification reduce bending moment and shear force, making the structure more stable and efficient. The second advantage is its high strength to weight ratio. The Warren Truss distribute load evenly across the structure, allow it to support relatively large load while using a smaller amount of material. This makes it suitable not only for real engineering structure but also for the lightweight balsa wood bridge model. So lastly, this diagram also highlight the zero force member. Although this member do not carry significant load under curtain loading conditions, and they also play an important role in maintaining the bridge geometry and improving overall stability and reducing the risk of buckling. So overall, this characteristic make the Warren Truss an efficient, lightweight and reliable structure system.
This flowchart shows the overall methodology used to design, analyze, fabricate, and test the Warren Truss bridge model. This the process consists of 11 main steps. For the step 1 is reviewing the project requirements. First, we review the project requirements, including the design specification, loading conditions, material limitations, and assessment criteria. This ensures that our bridge design met all the project objectives. Step 2 is selecting Warren Truss configuration. Next, we selected the Warren Truss configuration because it provides an efficient distribution of loads using a series of triangular members. This design offers good strength while minimizing material usage. And step 3 is preparing for the bridge design. After selecting the truss type, we prepare the bridge geometry by determining the bridge dimension, span length, member arrangement, and joint locations before beginning the structural analysis. Step 4 is performing manual structural analysis. We then carried out manual calculations using the method of joints. This allows us to determine the support reactions and the internal forces in each truss member, helping us to identify whether member was in tension or compression. Step 5 is developing step pro models. Step pro model. After completing the manual calculations, we created the SAM bridge model in Step Pro software. This software was used to perform a more detailed structural analysis. Step 6. Apply loads and supports. In Step Pro, we assign the support conditions and apply the requirement loading cases based on the project specifications so that the software could simulate the actual behavior of the bridge. Step 7 is evaluating structural performance. The software then calculated important structural parameters such as member forces, deflation, and overall stability. This result helped us assess whether the bridge design was structurally safe. Step 8 is fabricating truss bridge model. Once the design was verified, we fabricated the physical bridge model using balsa wood and adhesive, following the dimensions prepared in the design stage. Step 9 is conducting load testing. The completed bridge model was then tested by applying loads gradually until failure or until the required load capacity was achieved. This experiment allowed us to observe the bridge's actual structural performance. Step 10 is comparing and analyze the result. Next, we compare the manual calculation, step pro analysis, and experimental test results. Any differences were analyzed to evaluate the accuracy of the analytical methods and identify possible sources of the error. And finally, for the step 11 is preparing for the final report. Finally, all the findings were compiled into the final report, including the methodology, analysis, results, discussion, and conclusion. This slide explains the bridge model that we designed and the software used to analyze its structural performance before fabrication. First is the bridge modeling. The bridge was designed using the Warren Truss configuration, which consists of a series of triangular members. This type of truss is selected because it provides good strength while using less material. The total length of the bridge is 800 millimeters with an effective span of 700 millimeters. A 50 millimeter overhang is provided at both ends. Each truss panel has a length of 100 millimeters, resulting in 7 equal panels. The truss height is also 100 millimeters, giving a balanced structural geometry. For the support conditions, joint A is assigned as a pin support, which restrains both horizontal and vertical movement, while joint H is assigned as a roller support, allowing horizontal movement caused by expansion while resisting vertical loads. Next one is the software selection. Step Pro. Step Pro was selected as the structural analysis software because it is widely used in civil and structural engineering due to its accuracy and reliability. The software allow us to model the bridge, define the material properties, apply supports and loading conditions, and automatically calculate support reactions, member forces, stresses, and deflections. Before fabrication, Step Pro also enable us to verify that the bridge design is structurally safe and perform as expected under the applied loading. For the overall process, in summary, the Warren Truss Bridge was first modeled in StatPro using the specified geometry, material properties, support conditions, and loading cases. The software analysis results were then compared with manual calculations and the experimental load test. This comparison helped us to evaluate the accuracy of the structural analysis and the overall performance of the bridge model. In conclusion, using StatPro before fabrication helped us to reduce design errors, verify the structural behavior, and improving the reliability of the bridge design. That's all from me. Thank you so much.
Okay, so thank you to the previous presenter, Miss Ellie. Now, me myself, Azami bin Wahyu, will continue with the physical blueprint and fabrication toolkit. So, as you can see at the picture above, this is a blueprint of our bridge, which is dimension has an effective span of 700 mm with 50 mm offset by side. And panels, it has 7 equal panels, 100 mm each. Now for the toolkit, we use the balsa wood as a primary framework. Number two is hot glue and super glue as the bonding agents to keep the beams attached to each other. And lastly, we use threads as a reinforcement for structural stability at the joints. So as you can see at the picture above, there is a physical presentation of what could be as our bridge. Okay, to continue our presentation, now we move on into the constructing the digital twin instead. So the first step is the node generation. We define exact XYZ spatial coordinates to establish the primary set frame. Duplicate across the z-axis for depth and connect via the add beam tool from the upper chords, lower chords, and the diagonal webs. So step 2, custom material proofing. Bypassing standard steel or concrete databases, custom timber because the material we use is balsa wood. That's why we set it to timber. Then we can define it accurately, simulate the organic lightweight nature of the physical balsa wood, as I said before. And now, number 3 is the prismatic assignment. Rectangular prismatic profiles are assigned to the digital beams to perfectly mimic the cross-sectional dimensions of the physical balsa strips. You can also see the two pictures I put above, which is the representation of the material proofing and the prismatic assignment. Defining physics within the software environment. So there were 3 points, which is the first one is boundary constraints. We assign a pin support at one end and a roller support at the opposite node to perfectly simulate a simply supported beam. Now the second is load application. Establishing a uniform point load, establishing a uniform load distribution simulating self-weight, totaling a 0.048 kilonewton dead load applied across the structure. Now for the last one is engine execution. Initializing the perform analysis command, allowing the solver engine to process joint coordinates and solve the global element stiffness matrix.
Okay, for the internal force diagnostic provide ideal thrust theory, we're going to differentiate between the three parts, which are force vector, record metric, and also the engineering significant. Okay, first we go into the first part, which are Fx, as we are known as axial force, which the record metric of itself is peak 0.013 kilonewton, which already know is highly balanced on the low part, and also The crucial finding is on the record exactly 0 kN, which are perfectly demonstrating the theoretical is zero force member in state of equilibrium. Then we go to shear force, which is equation is Fy and also Fz, which the recorded metric is 0.01 kN, which is exceptionally low, and also it's proof the member are supporting load with a negligible shear effect. And lastly, for the bending moment is Mx, My and Mz, which are 0.00 kN, which are known as a virtually non-existent across all the components. And last, the verdict, which are the complete lack of flexure and shear, physically validate that the structure is operating efficiently as a true ideal truss system. Then the maximum deflection profile at the mid-span, which know as the maximum resultant displacement on our bridge, which are 31.460 mm, which are the deflection location which are noted at the 67 and 64. As all predict by the civil engineer like me, theoretically the center of the span are furthest from the main support, experience from the most significant deflection. And lastly, directional breakdown, which are vertically y-axis 31.455 mm, that proving the dominant force is gravity and dead load. And lastly, lateral x and z axis 0.452 mm, proving exceptional lateral stiffness and well distributed support.
Okay, next I can explain the synthesis of our structural analysis project, connecting theory, computation, and physical reality. Our analysis was built on three pillars, which is manual calculations using of method of joint, step pro, computation, and physical reality. Each approach gives us valuable insights into how structures behave under load. Regarding computational accuracy, our findings were significant. Step pro result align perfectly with our manual method of joint calculations. This proves two things. First, the software is reliable for structural simulations. Second, our fundamental understanding of structural mechanics is correct. This validation gives us confidence that our predictions of physical outcomes are accurate. Moving the load path efficiency, the symmetrical variant configuration performed excellently. The geometry transfer or loads to the support efficiently without twisting, instability, or excessive deformation. The variant naturally distributes force along the most direct path, minimizing stress on individual members. The most valuable lesson from this project is the geometry dictated stability. Understanding zero force members and axial load distribution is critical for design efficient, economical structure. Identifying zero force members save materials. Understanding load path prevents over-design. Appreciating geometry ensure safety. This is the essence of structural engineering, balancing efficiency with safety, theory with practice, and computation with physical understanding. Now I will share our recommendation for improving future designs based on lessons learned. First, enhance lateral stability. Lateral stability means the structure's ability to resist horizontal force like Y and seismic load. Many failures occur not from vertical loads but from inadequate lateral bracing. I recommend adding cross bracing or increasing the rigidity of frame connections to prevent buckling. Second, conduct better material profiling. This involves selecting materials with high strength to weight ratio while meeting deflection requirements. I recommend investigating alternative materials like high strength steel or composites, performing detailed deflection analysis to ensure all members meet serviceability standard. Third, strength connections. Connections are the weakest link in any structure. I recommend using thicker gas plates, high strength bolt or welded connections, and design redundant load paths so that failure at one point does not cause collapse. A structure is only as strong as its weakest connection. In conclusion, this project has reinforced fundamental engineering trust. Meticulous analysis leads to safer, more efficient structure. The alignment between manual and computation result give us confidence in our understanding, while our recommendations provide a path forward for improvement.